In the chapter we're going to start today, we're going to be seeing some more aromatic chemistry. Okay, so what we're going to be seeing are some different kinds of aromatic substitution reaction than what we've seen so far. And then we're going to segue into an area of great current importance, which is transition metal organometallic chemistry. And so we're going to be seeing some mechanisms of reactions that are very, very different from anything we've seen up to now in 272 or 273. The chapter is kind of broken up into two parts. The first part is before the organometallic chemistry, and then after that, organometallic. So let's take a look and see, first of all, what we're talking about here. Okay, so first of all, we need to know what an aromatic or an arrow halide is. So the arrow, when we say arrow halide, we're going to mean compounds that have a halogen directly bonded to the aromatic ring. So in other words, something like this, where I've highlighted the bonds of the aromatic ring to the halide, these would be arrow halides. Whereas trifluoromethyl benzene, which is, you could say, well, it's aromatic, it's got halogen. That's true, but that is not an arrow halide because it is, the fluorine is bonded to the sp3 hybridized carbon, not to the ring sp2 hybrid. So these are not arrow halides, even though they have an aromatic ring and a halogen. So when we say arrow halides, that's what we're talking about. Same thing for vinylic halides. When we say a vinylic halide, we're talking about a halide where the halogen is bonded to the sp2 hybridized carbon atom, not a compound that has a double bond and a halogen, but the halogen is bonded maybe to an sp3 carbon atom, as it is in these two. These two molecules have double bonds, they have halogens, but the halogen is bonded to an sp3 carbon atom. Okay, so why do we make the distinction? Well, we make the distinction because you get very different kinds of reactivity depending on whether the halogen is bonded to an sp2 carbon or an sp3. We've seen the reactivity of halogens that are bonded to sp3 hybridized carbon atoms, right? This was way back when we talked about SN1, SN2, E1, E2. Those were all reactions that took place primarily with halogens, but also with tosylates or other sulfonate esters that were aliphatic on the other end. And so now we're going to see reactions that take place with this kind of substrate. Now, I'm going to try to keep the nomenclature part of this brief, but yes, you do need to kind of know catechol, resorcinol, hydroquinone. Those are the common or trivial names for hydroxybenzenes. So depending on which substitution pattern you have, whether it's ortho, it's catechol, if it's meta, it's resorcinol, if it's para, it's hydroquinone. And these are names that you will see again and again, particularly those who are biologists, you'll see catecholamines and things like that. So you need to know what those are. Okay, so these are aromatic alcohols, all of them, right? We have an OH bond. In one sense, they're also enols, right? Because if I close my eyes and I kind of look at that, that looks like an enol. And in fact, we'll see that it has sort of enol-like reactivity in some instances. We've already kind of seen that, right? Because the hydroxy group strongly activates the ring towards electrophilic substitution. So in that regard, it looks sort of like an enol. But it has very different reactivity. The aromatic alcohols have very different reactivity from aliphatic alcohols, from alcohols where you have an OH bonded to a sp3 hybrid carbon. Okay, so how do they differ? Well, there's sort of a rule that you need to remember. That is no SN2 on SP2, okay? So you don't get SN2 reactions on arrow halides, you don't get SN2 reactions on vinyl halides. And so we'll see why. So in other words, if I had not a vinyl bromide here, if I had, say, bromoethane, then this reaction would work just fine. But as soon as that double bond is there, I don't get that substitution reaction at all. It just doesn't happen, okay? Now, why is that? Well, you need to take a closer look at what would have to happen to get that substitution, and then figure out why the transition state that you have to reach in order to get that substitution, why that transition state is high in energy, okay? So, the first thing you think of is, you know, you have a good leaving group and you have a strong nucleophile, right? I mean, so it looks reasonable until you start to think about it. Actually, that's true of a lot of things. So it must have something to do with the sp2 hybridization of the carbon atom that is bonded to the leaving group. I mean, that's the key difference, right? If it's ethyl bromide, the carbon atom is bonded to the bromine as sp3. Here, the only change we've made is we've gone from sp3 to sp2. So that has to be at the root of the problem. So now you have to imagine this ethoxy group acting as a nucleophile, not as a base, approaching this carbon atom, forming a bond from oxygen to carbon. There's that bond as it's forming, and then this carbon-bromine bond stretching out as it breaks. So as the transition stage, you approach the transition state, this carbon atom, which is the one that chemical change is taking place at, this one right here, that carbon is changing its hybridization. And it's going from an sp2 to an sp hybrid. It's an sp hybrid because now it's bonded fully only to two other atoms, a hydrogen here and a carbon there. And these are partially formed and partially broken bonds. Now, we've seen this rehybridization with the SN2 reaction. With the SN2 reaction, on the other hand, what did we have? We had an sp3 hybrid. That was the carbon atom that was bonded to the leaving group, undergoing rehybridization in the transition state to sp2 and then back to sp3. Here, unsurprisingly, it's going from an sp2 to an sp and it would have to go back to sp2. Now, it turns out the sp hybridization is about 5 kcals per mole higher in energy than sp2. So this will automatically raise the energy of the transition state by 5 kcals per mole, and that slows it down by about 10,000 times. So that's already bad. But then there's another problem too. The other problem is steric. And so in order for this kind of a substitution reaction to take place, the nucleophile ethoxide has to attack within the plane of the molecule. So remember for the SN2 reaction, what happened was you had the nucleophile attack the carbon atom from the back side, right? And then that carbon atom, sp3, kind of flattened out as you start to stretch the bond to the leaving group. And then as the reaction completed itself, it kind of was the umbrella in the wind, right? It just kind of folded back and became sp3, but with inversion of configuration. That was for the SN2 reaction. For this reaction, what would have to happen is that the nucleophile, ethoxide, will have to approach within the plane of the molecule. Remember, this is a planar molecule. And so this is the best case where I have a hydrogen here and a hydrogen there. And yet still, this is going to run into van der Waals repulsions as it approaches these two hydrogens. So anything larger than hydrogen, methyl, I mean even trivially larger, and that van der Waals repulsion becomes really bad. And so these turned out to be the reasons why it works the way it does. And I can say that, well, you know, why's that approach from the plane of the molecule? Here's why. The reason it has to approach from the plane of the molecule is because the nucleophile, any nucleophile, doesn't matter whether it's ethoxide or anything else, any nucleophile has an electron pair that it is donating to the atom undergoing change, right? And so that atom, in this case, it's not a cation, it's got 4 bonds to it. It's a carbon atom with 4 bonds to it. So the only place where the electron pair from the nucleophile can go is into an empty orbital. That empty orbital turns out to be the sigma star, the antibonding orbital that's associated with this sigma bond. That orbital lies within the plane of the paper, the plane of the molecule. And so that's why the approach has to be from behind within the plane of the paper and behind the carbon. Okay, so that's the situation that you have with a vinylic halide. So now the question is, well, okay, so vinyl halides don't react, but how about aryl halides? Is it the same situation? No, actually it's worse. And here's why. You have all the same problems, except that a nucleophile now would have to approach from inside the ring, right? Because for backside attack, as I've just shown, that would mean that the nucleophile would have to sit right in the middle of the ring. Can't be. That's bad. It's impossible, actually. The other impossibility is that once you did the displacement, of course, you're going to change the geometry of the double bond, and you're going to end up with a trans double bond in a 6-membered ring. Remember that doesn't work. And the reason it doesn't work is because that red bond in this ring would have to be completely strained to the breaking point. And so for those reasons, you're just never going to get a regular kind of an SN2, I'm sorry, SP2, no, SN2 and an SP2. That won't happen. Now, it turns out that vinyl halides and aryl halides do undergo elimination. And so the elimination reaction here actually does work, takes some heat. This is going to be a syn elimination, but it does work. And so you can eliminate vinyl halides just fine. That's no problem. Aryl halides also undergo elimination under really vigorous conditions, and we're going to see that reaction. That reaction, I'll kind of give it away right now, gives you also kind of an acetylene, right? So if I'm going to do an elimination of HBr here, then just as I eliminated HBr here and I got a triple bond, if I eliminate HBr here, by golly, I'm going to get a triple bond there too. But it's going to be kind of a weird triple bond, isn't it? Because look what has to happen. Let's just say this is a hydrogen atom that you're extracting with base. So I have some kind of base. We don't need to think about what that is right now. It comes in here and it does this kind of chemistry, just as we've seen for other E2 type eliminations. Then what I will end up with is this kind of a species, which is known as a benzyne. So the "-ine", remember, is the suffix for an alkyne. Well, here it is applied to a benzene ring. Now, this triple bond, I mean, we can draw anything we want on paper, but that triple bond is kind of a weird triple bond, isn't it? Why? Well, because if each of these carbon atoms is sp hybridized, like in a regular alkyne, then that triple bond should have a bond angle of 180 degrees here and 180 degrees there. And as you can see, if it's going to be in a 6-membered ring, there's no way. And so this triple bond is a very reactive and very different kind of triple bond from any one we've seen. So, to sum up, yes, you can do eliminations. Vinyl halides, no problem, because you can get the geometry here just fine, right? Here I have 180 degrees, but no, it's the normal kind of alkyne. Here, you don't get a normal alkyne. You get a very strange kind of reactive alkyne. And so, yes, it can be done. We'll talk about that sometime later during the semester. So that's the situation that we have with aryl halides and with vinyl halides with respect to SN2 reactions. They don't take place. Elimination reactions, E2 reactions, yes, but. Now, what about SN1? The SN1 reactions take place. And you already know the answer because of what we just said. No SN1 reactivity. So no SN2 on sp2, but also no SN1 on sp2. And so you can imagine taking now this 2-bromopropene and doing a solvolysis in ethanol to get a cation. Well, I can write that, but you know what? That never happens. And you can imagine taking bromobenzene and doing a solvolysis in ethanol. I can write that cation. That never happens. And so these reactions don't take place. Now, the problem is not the second step. I mean, if somehow you're able to get this cation, if somehow you're able to get this cation, and you form them in the presence of ethanol, hey, no problem, you get these just fine, right? Now the problem is making these cations. These cations just don't form because why? Because they're too high in energy. And so formation of these types of cations just costs you too much in terms of energy. On the other hand, if you're able to ever make them, yeah, they'd be really reactive. And in fact, there are ways to make those cations. We're going to see at least one of them in the future. But you make them in a very different way. When you do make them, they do react. They're extremely reactive. But you don't make them by solvolysis of a halide. That won't work. Now, why is it that it doesn't work? So we're going to take a look at cations like this first, okay? So take a look at this cation. Now, the way I've drawn that, the carbon atom I'm pointing to has a positive charge. And it has a positive charge because it lacks an electron pair. It's been the electron pair that it used to have now is bonded to the bromine, so you have Br minus with the electron pair after the solvolysis. So if I look at this carbon atom, it's bonded to 2 carbons, so it's sp hybrid, an sp linear hybrid. So that means that carbon, carbon, carbon form a 180-degree angle. Now the pi bond, I'm pointing, I know you can't see it, but the pi bond here still exists. And so the pi bond's still there. I didn't do anything to the pi bond, right? So the pi bond's still there. And I've shown it in this diagram with the colored in orbitals. I've shown the 2 p orbitals on each of these carbon atoms, overlap of which forms the pi bond. So the pi bond is there. The empty orbital, where the positive charge is, if you want to think of it that way, the empty orbital is orthogonal to this pi bond, because this is an sp hybrid. Remember, if this is sp hybridized, then it's got 2 orthogonal pi bonds. And so one of them is here, the other one isn't a pi bond, it's an empty orbital, but it's orthogonal. What that tells you is that there's no resonance stabilization for that cation. So this cation, don't fool yourself, this is not resonance stabilized. Neither is this one. We'll get to this one later. No resonance stabilization here. And so we can say it's not an allylic cation, right? So please don't make don't get confused and think that C, that this is absolutely not the same as this. Okay, those two are not the same. Here, the positive charge is on an sp2 hybrid. Here it's on an sp hybrid, so I should have shown this linear. But these are not the same thing at all. This is resonance stabilized. This is not. Okay, so no resonance stabilization. Why is this not resonance stabilized? Because there's no overlap between that empty 2p orbital and any other 2p orbital. And so that's one problem already. So we have a cation where we have a positive charge that is not resonance stabilized. Bad. But there's something else bad too. This carbon atom, not this one, but this one here is sp2 hybrid. And so the atom bearing the positive charge is bonded to an sp2 hybridized carbon atom, that one, and that inductively is electron withdrawing compared to an sp3. And so remember that sp2, the more s character you have, in the orbital, the more electron withdrawing it is. Well, here you have an sp2 hybrid bonded to the positively charged carbon atom. This is sucking electron density out of that carbon. And so, bad for two reasons. Not resonance stabilized, also bonded, think of it as just being bonded to an electronegative atom. That's what it is. So inductively it is being destabilized. So, bottom line, is what I said before, this doesn't happen. And it doesn't happen because it's going to cost you just way too much energy to break that carbon-bromine bond to form a vinyl cation. Vinyl cations are very energetic. Another reason, too, and that is maybe this factors in a little bit, and that is that the CsP2 bromine bond is stronger than the sp3 bromine bond. Remember that those bonds to hydrogen, but also to bromine, are shorter and stronger than they are in sp3. So if I look back at this molecule, the CH bonds here are shorter and stronger than the CH bonds there. Well, this carries over to the carbon-bromine bond that's bonded to an sp2 hybrid versus one that's bonded to an sp3. So you have every reason to expect that you don't that you're not going to see that kind of Solvalysis reaction. So now we go and take a look at the arrow cation. And I've tried to do the same thing for the arrow case that I did for the vinyl cation. So I've shown the sp2 hybrids all around the ring, and then I've shown the empty green sp2 orbital that is on a positively charged carbon atom. Now, remember that when I'm looking at this cation, remember that I'm looking at something that looks like this, right? So I've taken the bromine, and let's push arrows just so that we don't lose track of where the electrons went. So I'm taking this electron pair, supposedly, and this doesn't happen, so let's put a cross through it, but I'm taking this electron pair, which was shared between this carbon atom and that bromine, I'm giving it to the bromine. So now, the bromine is going to be negatively charged, and if I draw the ring, I'll have a positive charge here. But remember that I have hydrogens all the way around there. And so this cation is not the same cation that we saw when we did electrophilic aromatic substitution. Okay, so that cation from electrophilic aromatic substitution is a different kind of a species. Look why. So it helps, I think, the first time to show the hydrogen atoms. So imagine that I have now Br plus reacting with the benzene ring. And so this reaction does take place. And it gives rise to, let's put the hydrogen here, bromine there. It gives rise to this cation that I'm drawing for you. Now this cation is a different one from that one, right? Because you'll notice that the empty orbital here, you have to imagine it, is within the plane of the ring. And so this empty 2p orbital is, I'm sorry, it's not within the plane of the ring, it's above and below the ring, so it overlaps with these pi bonds. So this is resonance stabilized. So this is resonance stabilized. And this one is not, okay? And the reason it's not is to be seen right there, that empty orbital is orthogonal to all of the 2p orbitals in the ring. And so this one is within the plane of the ring, whereas this one is in a position above and below, one lobe above, one lobe below, to overlap. So So those two cations are very different. So here the empty 2p orbital overlaps. In the other case, it doesn't. Please don't confuse the two. Now, there are other problems with this too. First of all, you might question why in the vinyl case I said that, well, you know, the positively charged carbon has to be sp hybridized and linear with bond angles of 180 degrees. And here you'll notice I showed it in a ring. Well, you kind of know, because if I make this an sp hybrid, then I will have 180 degree bond angles, and that's going to again not be possible in that ring. You just can't do it. So that will introduce an awful lot of strain into that benzene ring, and that's just not sustainable. And so it has to be sp2 as a result. This has to be sp2 hybrid. And finally, it's the same thing that we saw before. You have a positive charge here bonded to now not one, but two other sp2 hybridized carbon atoms, which are electronegative, pulling electron density out of that cation. So it's destabilized through an inductive effect. So now that we've said all that, you think, well, you know, fine. You know, how boring, it doesn't react. But actually, you can get reactions of aryl halides with nucleophiles. And so, so we said that, you know, you can't get an SN1 reaction, but you can get a slightly different reaction. And so let's take a look and see. So this is called the nucleophilic aromatic substitution. So this is not an SN1, and it is not, I repeat, not an SN2 either. This is something new. And you can tell that it's something new because of how this works. Look at this. So if I take chlorobenzene, I could take an iodobenzene, I could take a bromobenzene, it wouldn't have made any difference. I can treat it with a very good nucleophile, methoxide, and you know what? Nothing happens. It sits there and it does not react. And it doesn't even react a little bit. There's absolutely no reaction. Now I'm going to do something a little different. I'm going to put a para, very important, a para, not meta, ortho or para, a para, nitro group. Now what do we know about the nitro group? We know that it is destabilizing for electrophilic aromatic substitution. So I put a nitro group on a benzene ring, and I do an electrophilic aromatic substitution, the rate goes way down. Why? Well, because the nitro group is pulling electron density out of the ring. So if I want that ring to act as a nucleophile, for example, towards Br+, then the nitro group is not helping, it's hurting. But here, I'm doing something different. I'm allowing the ring to react not with a positively charged ion, but with a negatively charged ion. And here, you'll notice that the nitro group helps. So here, I do get reaction. If I put a second nitro group in one of the ortho positions, then look at what happens to the rate. It goes up by about 1,000,000-fold. And if I put a third nitro group here, it goes up even faster. But the weird thing is that you would predict, okay, so, you know, maybe chloride doesn't react, but, you know, we know from SN2 chemistry that bromides react faster than chlorides and iodides faster than bromides. So what would have happened if I had an iodide here? Would that have worked? Well, no, it wouldn't have, but if you have a fluoride, if you have a fluorine compound, that's even faster than the chlorine. And so it looks as if things are kind of upside down here, because you expect the fluorine to be less reactive. You've been conditioned to think of that. Because why? Well, because the carbon-fluorine bond is stronger than the carbon-fluorine bond. So things seem to be the reverse of what we saw with the SN2 and with the E2 and the E1 and all of those. And why is that? I mean, this is a stronger bond than that one, yet this reacts faster. So that tells you something. What does it tell you? Well, it tells you that you're not breaking the strong bond in the rate limiting step. Okay? So the reason the stronger carbon fluorine compounds are slow to react in SN2 chemistry is because in the SN2 reaction, remember, the rate limiting step, that bond has to break. The fact that, that here the fluorine reacts faster than chlorine, faster than bromine, faster than iodine, tells you that we're not breaking this bond in the rate limiting step. The rate limiting step does not involve cleavage of the carbon fluorine bond. In fact, the carbon fluorine bond, because fluorine is more electron withdrawing than chlorine, this actually accelerates the reaction. So to figure this out, you need to remember why we have the reactivity series that we saw for the SN2 and for the SN1. And the reactivity series, you will recall, was that for SN1 and SN2, iodide faster than bromide, faster than chloride, much, much, much faster than fluoride. In fact, in most cases, alkyl fluorides don't react in SN1 or SN2 reactions. Here, it's just the opposite. Here, for the nucleophilic aromatic substitution, the fluoride is much faster than chloride, a little bit faster than bromide, a little bit faster than iodide. And so, in the SN1 and the SN2, the carbon-halogen bond is being broken in the rate-limiting step. So the inevitable conclusion is that in the aromatic substitution, you're not breaking the carbon-halogen bond in the rate-limiting step. So this is the SNAR, that's substitution nucleophilic aromatic. You're obviously not breaking that. So then the question is, well, what is the mechanism? The mechanism is one that we have not seen before. The mechanism is called an addition elimination. So, in other words, addition elimination mechanisms are exactly what they sound like. You do the addition of the nucleophile to some substrate, in this case an aromatic halide, and then in a second step, you do the elimination. Well, guess which step is going to be the slow step? The slow step is going to be the one where you lose the aromatic stabilization of the ring. And so the slow step involves the nucleophilic addition. That's the rate-limiting step. Now this makes perfect sense because you have to overcome that loss of aromatic stabilization. And you end up with this intermediate in the first step that's called the Meisenheimer complex. You don't need to remember that name. But this intermediate is resonance stabilized. It's an anion, negatively charged. It's not the same intermediate that we saw for the electrophilic aromatic substitution, which was a cation. This is an anion. However, the resonance structures look very similar, except they've got a negative charge. Now you can see why the para position had to be the one that has the nitro group. Why is that? Well, because I'm doing a substitution of this fluoride, right? So the nucleophile has to attack this carbon atom. That leads to a negative charge on the adjacent carbon atom, which I can delocalize all the way into the nitro. This, of course, is going to be the important resonance structure of all four of them. Because why? Because all atoms, have a complete octet, and the negative charges, if you will, are on the most electronegative oxygen atoms. And so I'm not going to be able to end up with this kind of a very stable resonance structure unless the nitro group is either para or ortho. If the nitro group is meta, I'm not going to have this resonance structure. So, bottom line, in order to accelerate the SNAR reaction, in order to get a fast nucleophilic aromatic substitution reaction, I need to have the electron withdrawing groups either at the ortho or the para position. The more electron withdrawing groups, the better. Okay? So, what's the role of fluoride? Well, why is fluoride faster than chloride? Well, because fluorine is more electronegative, right? And so the fluorine pulls electron density out of this sigma bond, and so it induces a delta plus where I'm pointing. It also stabilizes this intermediate by an inductive effect. And so the fluorine is actually helping out. And it helps out by lowering the energy of the transition state just through an inductive effect. It does that better than chloride because fluorine is more electronegative than chlorine. So that's why the fluorides react faster than the chlorides. Okay, now this is the first step. What is the second step? Well, the second step is the step in which I spit out F minus from this Meisenheimer complex. Now that turns out to be a fast step. The second step is faster than the first. And it is faster than the first because I'm restoring the aromatic stabilization of the ring. And so Hammond's postulate kicks in one more time, and we have a stabilized transition state for the second step because aromaticity is being restored. Now I can say that, well, gee, you know, but still, look, I'm breaking a strong carbon-fluorine bond. So if I had iodine there, wouldn't that second step be much faster? And the answer is yeah, it would, but it doesn't matter. And the reason it doesn't matter is because the second step is not rate determining. Remember, it's the slow step. You have a multi-step reaction. It's the slowest step that determines the overall rate. And so that, in this case, is step number one. Step number two, we don't care about. That can be fast, that can be slow. It's never going to be as slow as the first step. It's always going to be faster than the first step. And so if it's faster with iodine, it doesn't matter because the first step is the one that determines the rate. So this just states what I said before, that the reason that the nucleophilic aromatic substitution reaction of fluorides is faster than chlorides, faster than bromides, faster than iodides, is because the electron withdrawing effect of the fluoride stabilizes the Meisenheimer complex and through a polar inductive effect. So this is an interesting reaction. It's actually useful, and it works. By the way, from your book and also from my example, you may think, well, how useful can it be? It only works for nitro compounds. No, it doesn't. It works for lots and lots of other kinds of compounds too. They just have to have electron withdrawing groups. And so any one of the groups that deactivates a electrophilic aromatic substitution will activate a nucleophilic aromatic substitution, right? So nitro is activating, sulfonyl is going to be activating multiple fluorine atoms on the ring, activating. And so it's kind of the reverse, but it has to be, right? Because now we're stabilizing an anion. Okay, so that pretty much is the first short part of chapter 18, where we talk about nucleophilic aromatic substitution and the fact that the substitution chemistry of sp2 hybridized carbon atoms bonded to leaving groups is very different from sp3 hybridized carbon atoms bonded to leaving groups, which is what we saw in our chapter on SN1, SN2, and all of that stuff. Now, it turns out that vinyl halides and aromatic halides, but also vinyl tosylates, triflates, heterotriflates, tosylates, they have a very rich chemistry that we're going to talk about next that does not involve the normal kinds of reaction mechanisms that we've talked about. These are reactions that are catalyzed typically by transition metals, which brings us to a discussion of the first row of transition metals. So we don't have we used to have a periodic table in this room, but I've reproduced the row that we're going to be interested in. You don't have to, oh, we do have one? Oh, yes, but only half the classroom can see it. Huh? Oh, there's one there too. Good, okay. So you guys can see it. Okay, good. So, I've reproduced that first row, and it starts with scandium. They have these numbers. And the numbers correspond to the valence electrons in the neutral atom. Okay? Now, these metals, and these are all metals, by the way, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. These are metals. They all have d orbitals. We've got 5 d orbitals, so we don't have an 8-electron hole anymore. So remember that we have this 8-electron hole octets and all that. That goes out the window. Why? Well, because now we have additional orbitals to put electrons in. And so now we're going to see that we have something that's called the 18-electron rule. Okay. So the first reaction I want to talk about is known as the Heck reaction. Jim Heck shared the Nobel Prize a couple of years ago, no, more than 2 years ago, I guess maybe 3 years ago, with a couple of other people for this discovery. He died in 2015. Unfortunately, he died a very poor man. But I had the pleasure of hearing him talk a couple of times, and I think when he discovered this reaction, nobody really appreciated in the early years. Nobody really appreciated how important it was. It just seemed like some obscure little thing, and yet this reaction and the ones we're going to talk about have kind of transformed how we inter alia, how we synthesize drugs. And so for pharmaceutical manufacturing, this has been just an absolute revolution. Okay, so let's take a look at what goes on here and then see how different this is from anything we've seen before. So we have an aryl halide, okay? So there is some reactivity, obviously, associated with this carbon-bromine bond. And we allow this to react with ethylene, a gas, but something that has absolutely no functionality, right? We just have, it's a hydrocarbon. It's an unsaturated hydrocarbon. But, and so if we just take these two reactants and we mix them up and heat them and put them under pressure or whatever you can think of, absolutely nothing happens. They don't react. But in the presence of a catalytic, this cat means catalytic, amount of palladium, you'll notice that the palladium is underneath nickel. I'll get to this in a minute. And triethylamine in a solvent at a high temperature, so this has to be done in a sealed apparatus for 18 hours. We end up getting a carbon-carbon bond highlighted in red with the amine hydrobromide salt. And the yield is absolutely excellent. Now, it's important to notice that the palladium is present there in truly catalytic amount. What do I mean by catalytic amount? Well, anything that is less than 1 molar equivalent is catalytic, but here we're talking about, less than 1%. So you don't need very much. Sometimes you can do these reactions with, maybe, 0.01%. And so they really are catalytic. And so we speak about catalyst turnover numbers. What is a turnover number? Well, here, let me give you an example. Let's just say that you got 100% product with 10% catalyst. Then the turnover number for that catalyst would be 10. Because it would mean that each catalyst molecule was responsible for forming 10 molecules of product. If you got 100% yield with 5 mole% catalyst, then the turnover number would be 20. And so on. Okay, so these reactions have typically pretty high turnover numbers. Now let's talk a little bit about the palladium. Now you'll notice that the palladium is associated with 4 of these triarylphosphine groups. And let me draw this out. I've drawn this out in shorthand. This is a big molecule. It is, so this would be triphenylphosphine. We've seen triphenylphosphine in Chem 272. Triphenylphosphine is a very common, is very commonly seen in these organometallic reactions. But this is a triphenylphosphine where I have methyl groups attached here. And this whole thing is going to be called a ligand. Okay, so this is a ligand. And it is bonded, in a sense, to the palladium, but non-covalently. Okay? So this is kind of a strange kind of a situation. You have this, these are neutral molecules, right? These are not, this is not charged. So there's no charge there. The palladium also does not have a charge. So that means if the palladium doesn't have a charge, that means that it is what? It is zero valent. So it has the same valency as it would have in a far palladium metal. Okay? So you look at this reaction and what's happened. Well, I've taken this aryl bromide, I've allowed it to react with ethylene, and I've gotten this product by, in a sense, subtracting hydrobromic acid out of these 2 reagents. So there's the HBr. The Br came from here, and the H came from one of those protons in ethylene. Now this is not an SN1 reaction. You know that because SN1 doesn't work on aryl halides. It's not an SN2 reaction because you know SN2 doesn't work on sp2. And it's not an SNAR either because we don't have a strong nucleophile and because we don't have any electron withdrawing groups on the aromatic. So this has to be something different. And this is an archetypical transition metal catalyzed carbon-carbon bond forming reaction. So a lot of these transition metals are going to be bonded, I said non-covalent and then covalently to ligands. But you can think of these as just being electron paired donors. So remember that the triarylphosphine has a electron pair right there. And so what you think of is this electron pair being shared now by the phosphorus and the palladium. On the periodic chart, you saw that palladium was right below nickel, right? And we said that nickel has how many electrons? 10 valency. Palladium has 10 valence electrons. I have 4 of these phosphines. Each one of those phosphines has how many electrons to donate to the palladium? 2. 4 times 2 is how many? 10 plus 8 is the 18 electron hole. So this is an 18 electron complex, okay? And so we're going to learn how to do this counting later on in this chapter. But the thought I'm going to leave you with is that ligands can be neutral, as we saw here, or they can be charged. And how we count electrons and how we determine metal oxidation states is going to be determined by whether the ligands are charged or neutral. So I will see you all on Friday.